So for chapter 8, it's going to be focusing on equations of rotational kinematics. And you already know that it's super similar to linear kinematics. I put up a graph for you guys of comparing rotational and linear motion and rotational motion with alpha or acceleration being constant. And you see there that it's the same big 5. And below I just put what it means when you're comparing it using the symbols of rotational and linear. Okay, so let's check our understanding. Since you guys pretty much already know what linear kinematics is, we're just going to be applying it with rotational kinematics. So if the blades of a ceiling fan start from rest, there's our initial, and after 2 revolutions, which is our displacement, and has an angular speed of 0.50 revolutions per second, that's our final velocity, then the angular acceleration of the blade is constant. So you already know from there it's constant. You can pull out the big 5 and you can use that. What is the angular speed after 8 revolutions? So we know our initial is 0, we know our theta is 2, and we know that our final is 0.5. And our units throughout this whole thing will be revolutions per second. So we can use the W final squared equals W initial squared plus 2 acceleration times x, or theta. So we just plug those in, which would be 0.5 squared equals 0 squared plus 2 alpha t 2. So we're just trying to find acceleration here. Or you would need acceleration to be able to find out what the final velocity is, so you just figure it out based on different, now that you have 8 revolutions instead of 2. So we already know acceleration based on dividing by 0.25 divided by 4, and it's going to give you the angular acceleration of 0.0625, but that's only after 2 revolutions. So what happens after 8 revolutions? So we can plug in the same formula, but this time we're going to be solving for the final angular speed, because you already know regardless of how many revolutions that they started from rest. So you would be W final squared equals 0 squared plus 2, the new angular acceleration, because it's constant, so it can still be used regardless of the revolutions, and this time that you're looking for 8 revolutions instead of 2. So you multiply 2 times 0.625 times 8, and then you're just going to find the square root of that, and that conveniently gave you 1. So the initial final velocity would be the final angular velocity would be 1 revolution per second. So let's look at a problem. A figure skater is spinning with an angular velocity of 15 radians per second positive. She then comes to a stop over a brief period of time. During this time, her angular displacement is 5.1 radian. Determine A, her average angular acceleration, and B, the time for which she comes to rest. So we already know our final based on having 15 radians per second here, positive, and we already know our initial would be 15 radians per second. Our final would be when she's coming to a stop, and it already tells us our angular displacement of 5.1 radians. So we lay everything out. W initial equals 15, W final equals 0, and theta equals 5.1. But you don't know the average angular velocity and time. So for A, you're going to be focusing on finding acceleration. So if it's saying that our 0 is our final and 15 is our initial, we can use W final squared equals W initial squared plus 2 alpha theta. So 0 squared equals 15 squared plus 2 alpha 5.1. So you do the math and you get negative 225 equals 10.2 alpha, and you divide that by 10.2, and your alpha would be, or your acceleration would be, negative 22.06 radians per second. Squared. Okay, so now that we know our theta is 5.1, and we already know our acceleration, and we already know our initial and final, we can find time by using theta equals final velocity plus initial velocity over 2 times t. So since our final velocity is 0, we're just going to have 15 as our velocity over 2. T equals 5.1. So then you would end up dividing 15 divided by 2, which would give you 7.5, and you're dividing that with 5.1 divided by 7.5. So your time would give you 0.68 seconds. So let's look at the last one. If a gymnast is performing a routine floor in a tumbling run, she spins through the air, increasing her angular velocity from 0.30 to 5 revolutions per second while rotating through 1/2 of a revolution. How much time does this maneuver take? Okay, so if it's 1/2, you already know 1 revolution is going to give you 2 pi. So I don't know if you guys have learned unit circle. Probably already have. If it's already half, you know at that point you're going to be at pi, or 180 degrees. So how much time does it take for this maneuver? So you already know that theta equals pi radian, and you know the initial velocity equals 3 revolutions per second, and you know the final velocity is 5 revolutions per second. What's the time? So this is not constant acceleration. There actually is a change. It's going faster at the end. So you have to convert from revolutions to radians because it's asking for it in time, and revolutions does not give it to you in time. So I put 3 revolutions per second and then 2 pi equals 1 revolution, converting it to 18.85 radians per second, and I did the same for the final, which would be 5 times 2 pi, which would give you 31.42 radians per second. And using that, you can use theta equals final velocity plus initial velocity over 2 times t, or pi equals 18.85 plus 31.42 divided by 2 times t, and then you would do 3.14, or pi divided by 25.13, giving your time 0.125 seconds. So just keep in mind that you're just going to be using the big 5 throughout this whole thing. You're just going to be changing the variables. I've been saying this for the past couple videos, that you just have to understand what the units are. The same thing, acceleration is always squared, radians is always something per second. So this time, if velocity is radians per second for velocity, radians per second squared would be for acceleration, and for theta it would just either be in radians, and this time will still be in seconds. But also it can change if they're asking for revolutions, but you just have to keep in mind that this is squared, this is not squared. No, sorry, this isn't squared, this isn't squared, this is squared, this is singular, and then time will always stay the same.